Okay, so we will so this week we will begin the topology of orbifolds. Basically we cover the introduction and compact actions in the first class, and then second class we do the definition of orbifolds, examples of orbifolds, and the abstract definition as a Lie groupoids. Okay, so topology of orbifolds. So it's important to understand the compact group action. So we will cover the orbit space, tube and slices, and path shifting and homotopy, covering homotopy and the locally smooth actions, smooth action, and the equivariant triangulation and Newman theorem. And then the definition of orbifolds, local groups and examples, and the definition is Lie groups, Lie groupoid. Okay, so it's here again, the groupoid means something else than what I said at the beginning. So again, the reference is a Brandon introduction to compact transformation groups. So this is a Springer. So I wrote academic, but you can download it again. And then the Shang has this book of homology theory of topological transformation group. And Illman, he wrote the first smooth equivariant triangulation of G manifold for G finite group. Okay, so that's some references. Okay, so what is a compact group action? So of course, just start with G. Just let's say G is just the group, then the G times X goes to X with EX is X. EX is X for all X, and GHX is G circle HX. So this is a left action. So group action means that it satisfies these properties. So there's a homomorphism from G to the homeomorphism group of X, right? So that the project operation is so product is composition here. Okay, so that's what the group action means. So actually we need the result for finite groups, but actually we will do for all the compact groups for a while. So equivariant map phi x from the y is between G spaces. So x and y are both G spaces. Is that the map so that phi gx equal to G phi x. So G and phi commutes for all G. And so that's the equivariant map. And the isotropy group is Gx elements of G which fixes X. So given X, you want to look at all the elements which fixes it. And so this is again a group because if you do any composition, then this composition will fix X, and then inverse will also fix X if G fixes X. If you multiply by G inverse here, then you get G inverse here. Okay, so that's the subgroup, and the G of a stabilizer of Gx. So X is moved by Gx is just a conjugate of Gx by G times G inverse, and then also Gx is a subgroup of phi x. Okay, G phi x. Okay, so if you map something to X to another space Y, then this stabilizer of image point is going to be in general bigger than just Gx, right? But of course it could be equal, but in general it could be bigger. So one of the fundamental theorem is Tichy-Gleason. So G, a compact group acting on X with the closed invariant set A, let G also act on the linearly on Rn. Then any equivariant map from some closed subset of A to Rn extends to the whole space. Okay, so you can always extend. So this is like so if you have just no action, and then so this is just an ordinary topological theorem, right? If G was a trivial group or trivial action. But for compact groups, this can be done for compact group action also. Okay. We're not going to prove that. Of course, that's in the Breton. And the next important thing is the orbit space. So you take any x, and then the gx is the image of x under the or the maps. Okay, all the elements of G. So you fix x, and then you look at all the image under as you vary the G elements. Okay, so that's the orbit. And then the G mod Gx is going to be one-to-one and one-to continuous function. So, so you mod out the G by the stabilizer, then this is one-to-one and one-to, right? Because if you take any coset here, right coset, then the then then the image is the same as long as stable uh, right. It should be the right coset space, right? And then if you take any element and then you multiply by a left coset space, right? Left coset or right coset. Yeah, right, left coset. So if you take any left coset, then any it doesn't matter which element. So if you have some C times H is in GX, then you can change H because it's in GX. Okay, so that gives you a well-defined map, and it's onto because you can see that this map from G to GX is onto, and also you can show it's continuous as well, right? Uh, so orbit type is given by the conjugacy class of GX in X. Okay, so because this is a conjugacy class, okay, and the orbit types form a partially ordered set. Okay, so because these conjugacy classes will form a partially ordered set, right? So the uh, uh, right. So it just means that some orbits. So you have to order by the fact that this orbit is a subset of. I mean, well, I mean, you have to look at the conjugacy classes and then consider that as a set, and then you can give a partial order based on the uh, what uh, right, cosets will have some relations among them. So that's how you can. I mean, G axis will have subgroup relations, and that will give you a partial order set. Okay, right. So G axis has subgroups. Subgroups are always partially ordered set inside the group. So that's what they're using. So so we write by G mod X. So this is a space of orbits and give a quotient topology. So what I mean is that you look at the list of all the orbit spaces. So orbit space, one orbit is a one element. Okay, so you quotient by any two elements at the equivalent if it's in the same orbit. Okay, so you quotient out by the fact that any two elements are equivalent if they are related by Z. Okay, so uh, then you take the quotient space. Okay, that's the quotient topology. And for any x GA, so this is an orbit of a set, in fact. So you can look at all the union of the images of A, and then you take the union. Okay, so that is sort of a orbit of the set. Okay, it's not orbit of point. So then this is a saturation of X. Okay, so on the quotient topology, the saturated set is you take the image and then you take the inverse image. So that's called the saturated set, right? So so GA will go, it will be a saturation of A. Okay, so saturation means that you push it to the quotient space and then you pull back. Okay, so so that's because any element equivalent to A must be in some it will be of this form, right? So something related. That's right. So the property is that X goes to X mod G is an open and closed and it's a proper map, right? Of course, so you do need the G being compact here, otherwise it's not going to be really true. And XG is a Hausdorff space. when G is also compact, right? So we need actually G being compact here. And X is compact if X mod G is compact. Okay. Again, you need G compact here. Otherwise, it's not true. Okay. Okay. And X is locally compact if and only if X mod G is locally compact. Okay. So on the assumption G is always compact. Okay, so up to here is true for any G, but from here, this property you need G being compact. So I didn't write that down. Anyway, so it's a sort of elementary effect in the Braden, so I'm not going to really prove that. So as an example, so let's take G times Y, okay, and then so action of G on Y is trivial. You just act by on the left side. Okay, so then that's fine with that. And another example is so that's probably very trivial example. So most of the example will be sort of a quotient of G times Y, but we're not going to prove that, and at least locally in many good cases. So let's look at the action of a secret group of order K on S3 in C2. So you consider S3 as a unit sphere on C2, which is R4. And so it has a complex corner, so you can multiply by these matrices. So then the quotient will give you a length space. So this is sort of explained in the Hatcher's book, so I'm not going to cover that. But we can also consider S1 action. So we can put in any ki theta and then 2 pi qi theta. Okay. So of course theta is in 0, 1. But you have that 0 and 1 are in the same orbit. I mean, give you same elements, so it gives you S1 action. Okay, so it gives you compact group action on S3. So then you can see that it has a 3 orbit type. So if you look at C2, if first corner is 0, then it's only acted by the 2 pi qi. So it will. So the period is when it becomes identity after some time. So it will become. So at 1 over q it will become identity again, and 2 over q it will be identity again. So that's how it acts. If you set the first corner 0, and then if you set the second corner 0, then it's so it will have a k period. Okay, one k period for that, and then so if you have both corners not 0, then it will have a kq period because it will come back to itself only. Sorry, it has actually 2 pi q period, so it doesn't come back to. So S1 will act faithfully, and then the other orbits it won't act faithfully. Right, so it has 3 orbit types. Okay, so that's important. So it's so it will have some stabilizer. Right. So I should say it has a different stabilizer for these 3 different types of orbits. Right. So there's a circle where the first corner is 0, and then there's a circle where the second corner is 0, and then the both corner not 0. Then there's another there. So the first when the first corner is 0, then it will have a stabilizer which is GK, and then the second corner is GQ, and the second corner is 0, then it will have order GK. Okay. Right. So in general, there's action of torus action on Cn. Okay. So it takes C1 to Cn. Ci are in complex unit numbers. Okay. And the yi's are in C and C, so these are all complex numbers. And then if you restrict the Ci to be 1, then this is S1, so you have n of these, so you get the Tn action here. And so you multiply by this number. So Tn will act on Cn in this way. Okay. And of course, it will act on the S2n minus 1, which is a unit sphere in there. Okay. Okay, so that gives you an actual example of action. Okay, so then so there's a homeomorphism from these Cn ma Tn to R plus n. So R plus n is R plus is I'm denoting by the so non-negative numbers, right? Non-negative numbers times n. So you send y1 to yn from Sn to the norm here, norm of these bonus. So then this orbit space and this is the same homeomorphism, this spaces. So orbit space can be identified with this. Okay. And so this is like what you call the corner manifold, right? So whether you are on some so standard subspaces, right? So you take an intersection with standard subspaces and it will give you some standard subspace in Rn plus R plus n, right? So it will have lots of different weird corners, and you can think of it as a polyhedron and with many different sides. Okay, so if you take the interior of these sides, then this will give you different type of orbits. So it's has a different type of stabilizers element. Okay. And of course, the interior has a interior of the everything is non-zero, then it will be the most general type of orbit, right? So and then if you have one or two is zero, then this will have different type of orbit and so on. So actually, this is a good example that appears in toric geometry. So you can see that in some toric geometry examples. And so when H is a subgroup of a Lie group G, then the left coset space is also so then the G acts on the right, right? So if you take the left coset space, then G will act on the right. Okay. So of course you have some quotient topology here. And then also if you take G mod Gx to this orbit space Gx, then there is a homeomorphism if G is compact. Okay, so I maybe I said that before, but you don't need the compactness here. So next I will give you the twisted product. So let X be the right G space and Y left G space. Then you can give your left action by GXY. So XY is an X times Y, right? By multiplying by G G inverse to the right and then the GY. Okay. So this is a left action and then you take the quotient on this space. This is called the twisted product. Okay. So people call this twisted product because so for each point of X, you kind of see a Y quotient by so you can actually map this to X where the fiber is like a Y quotient by G here. So it's kind of a fiber bundle type of picture. So in general, if you have a X go to B is a principal bundle with G acting on the left, and F is a right G space, then F twisted product GX is a associated bundle. Okay, so again, this is a what you call the twisted product. So this is an example of a twisted product. Right, this is a twisted product, and it will sort of again be a fiber bundle over B with the fibers homeomorphic to F. Okay, so that's the basic example of orbit space. So I mean, orbit spaces are not always good, and some bad examples are like corner and Floyd examples. So there's a GR action for RPQ with PQ relative prime on Euclidean space of some large dimension without any stationary point. So stationary points mean that so it's fixed on the every group element. Okay, so some elements will have fixed point, but not simultaneously on one point. Okay. So I will skip this proof. I don't think it's necessary. And then of course, Shang and Shang, they show that if G is any compact connected non-abelian group, then there is action of G on Euclidean space of sufficiently high dimension, which fixed point set F has any given homotopy type. So you take any group like this, and then any homotopy type, then you can find the action where the fixed point set has this given homotopy type. So that's a kind of an example. Okay, so F could be example, for example, empty type. So then this G will act without any fixed point, common fixed point or stationary points. Okay.